Right, so we are back to thinking about molecular orbital theory, so we can start thinking about polyatomics. If you remember earlier, we did diatomics, so thinking about just two of the same things, or maybe two different things that were connected. But what happens if we have like something bigger, like a triatomic? We didn't have an easy way of dealing with that before, so that's what we're going to get to. But before we get there, I just want to go over some of the brief tenets that we're going to have to use for molecular orbital theory. So make sure you go back. This was from Housecroft and Sharp, chapter 4 for the readings here. So make sure you've looked over that, and we had some videos, I think, back in week 4 for this. So go back and review molecular orbital theory because I'll just kind of assume that we remember that. So why are we doing this? Because again, what we're after is an alternative to valence bond theory. Valence bond theory has some quirks to it that we didn't like. So for example, we had to end up making these hybrid orbitals that we used, for example, in orgo, which were a little bit messy. Another part of valence bond theory is just the idea of having something like a Lewis structure to begin with. That was something that doesn't really jive well with quantum mechanics because we are localizing electrons at this point. So we want something that is going to do a better job of showing the reality of how molecules actually bond. The big key thing that we're going to be trying to do is now look at our molecules. Like, for example, here I've got benzene here, and now we see that we have these orbitals that are spread across the entirety of that molecule. That takes away the problem of localizing electrons, so it jives better with quantum mechanics in that regard. And quantum mechanics is probably a better solution. I would say it's more elegant because it's mathematical. There you can actually prove it. You don't have to do this jinky argument about, oh, well, if you add an S and a P, you can form them into this tetrahedron and kind of get all icky there. But we can actually use this in the Schrodinger equation. That works very nicely. And what's really great is it matches experimental results, which we had problems with this valence bond theory. So just as a reminder, how do we actually find these molecular orbitals? Well, these are just our molecular wave functions, and we're constructing them from what we call the linear combination of atomic orbitals, the LCAO. Mathematically, there's nothing too crazy here. This is just saying that our total wave function, psi over here, can just be written as a sum or difference of two different wave functions, or really we can do this as many as we want. And we're going to use this C value as an adjustable coefficient so that we can intensify one wave function versus another if we need to, so that we can make the orbitals that we want. And we're going to use this from our atomic orbitals that we're very familiar with. So the shapes of the S, the P, the D, and the F, we're not throwing those out. We're saying, hey, let's use those as our basis for our total wave function. So how do we add all of these orbitals together to form those molecular orbitals? That's the goal of this, and that's why it's going to be a really robust theory, because we're building it off of all these useful pieces. There are a few conditions for us to use linear combinations, specifically that the orbitals must have the same sign of the wave function when they overlap to give us some sort of bonding interaction. So, for example, if I have the positive lobe of one orbital overlap with the positive of another, that is a linear combination I can do. That leads to bonding. Same thing as with the negative. If a negative overlaps with a negative, that leads us to a bonding interaction. If we don't have the same sign, for example, we have a positive negative or a negative positive, this is how we get to an anti-bonding orbital. We also said that orbital energies must be similar for them to be combined. So if they're way far in energy, or we find that no orbitals can overlap for symmetry reasons or thinking about energetic reasons, this is how we end up with a non-bonding orbital. So that's where that's going to show up. Final consideration here is that atomic orbitals must be in quote-unquote close proximity in order to form a linear combination. That's a really loose description here, and it really depends on the structure. There are no hard and fast limits here, but you can assume that a molecular orbital is going to form from things that are close. So if you have two s orbitals that are close together, yeah, that could be a good molecular orbital. But if you have a molecular orbital that you're forming from an s orbital here and an s orbital here, is that going to be good? Question mark, because how well are they going to actually be able to interact? That's a question for PChem, though. So we'll leave that alone. Our overall goal is to end up creating a diagram of some sort that kind of looks like what I've got here on the left-hand side. So remember, this was for our diatomics. Could have been something like oxygen. So it had two oxygen atoms. We started in saying, okay, we've got our s orbitals that are going to mix to form our two orbitals down here. We've got our two s here. We've got our two p here, and they're all going to add up to form our molecular orbital diagram. One of the things that we ran into here and why we liked molecular orbital theory is we recognized that O2 has a total of 16 electrons and was paramagnetic. And as we start filling in our electrons into our molecular orbital diagram, we see that those unpaired electrons are actually shown. They're up here in these antibonding orbitals. This was now showing that comparison to experiment that actually works. We had some basic terminology. We said, for example, there was the highest occupied molecular orbital. So this is where we find two electrons in these pi g star orbitals. That was our highest occupied molecular orbital. We also had the lowest occupied, the LUMO here, and we see the next level that doesn't have electrons is the sigma u star state. So we have ways of categorizing these and giving them names. So hopefully you remember some of that. If not, definitely review those videos from previously in the semester. But really the question that this is going to drive us to, well, what do we do with larger molecules? I mean, I think we start realizing there's a problem. Here I'm dealing with oxygen and oxygen. I've got two sides for a diagram. What happens if I have something like a linear triatomic? How do we fit a third piece into our diagram? So that is the big question that we're going to have to deal with in our upcoming videos. So that's just, again, to be a quick review over stuff. If any of this stuff doesn't make sense, definitely go back and review the content videos from earlier. Make sure you go back over the reading. And as always, ask questions. That's how we learn from this stuff. All right. So until I see you next, be excellent to each other.